Scientists have recently uncovered an extraordinary mystery that challenges our understanding of the universe's infancy. A massive black hole, formed only 400 million years after the Big Bang, has been discovered, defying conventional astrophysical theories. This finding is not just a statistical anomaly but a paradigm-shifting revelation. It compels us to reconsider the mechanisms that shaped the early universe. How could such an immense structure emerge so quickly after the universe's inception? What factors warped the cosmic timeline to allow this rapid formation? Join us as we unravel the enigma of these early cosmic giants and explore the groundbreaking implications of their existence. The James Webb Space Telescope, JWST, has become a cosmic detective, uncovering secrets of the universe with unprecedented clarity. Among its many discoveries, the detection of a supermassive black hole in a galaxy known as CS 1019 has captivated scientists. This black hole formed when the universe was just 400 million years old, a time considered too early for such massive objects to exist according to prevailing theories. With a mass millions of times that of our Sun, CS 1019's central black hole challenges every established model of black hole formation and growth. Imagine the early universe as a chaotic playground, with stars and galaxies forming, colliding, and evolving. The discovery of CS 1019 hints that some regions of the cosmos were operating on a fast-forwarded timeline, producing these massive entities well ahead of schedule. This phenomenon raises fundamental questions. Was the universe more efficient at forming massive structures than we thought? Or are we missing crucial pieces of the cosmic puzzle? The discovery of CS 1019's black hole is not an isolated event. Alongside it, two more black holes have been identified in galaxies CS 2782 and CS 746, each weighing around 10 million solar masses and forming roughly a billion years after the Big Bang. These black holes belong to a family of 11 early galaxies, each offering unique insights into the universe's early days. Collectively, they reveal that the universe's rules during its formative years were far more complex than previously understood. One key mystery is how these black holes grew so massive, so quickly. Two leading theories offer potential explanations. Direct collapse black holes. These black holes may have formed directly from the collapse of enormous gas clouds, bypassing the intermediate stage of star formation. Such a process would allow them to grow rapidly without waiting for stars to evolve and explode as supernovae. Hyper-efficient accretion. Alternatively, smaller seed black holes could have rapidly devoured surrounding matter, growing at unprecedented rates. This scenario suggests that the early universe provided an exceptionally fertile environment for black hole growth. The universe's early years were a period of intense activity, characterized by frequent galactic mergers and rapid star formation. The JWST's observations reveal that galaxies like CS 1019 were teeming with new stars and undergoing violent interactions with neighboring galaxies. These events likely fueled the growth of their central black holes, creating a feedback loop where black holes and galaxies evolved together. For example, spectral data from CS 1019 suggests that its black hole's growth was driven by a dramatic galactic merger. Imagine two galaxies colliding, their combined gravitational chaos funneling vast amounts of gas into the black hole's accretion disk. This high-energy environment would have provided the perfect conditions for rapid black hole growth. The implications of these discoveries are profound. For decades, scientists believed that massive black holes required billions of years to form. Yet, the existence of CS 1019 and its counterpart suggests that these objects were thriving in the chaotic environment of the early universe. This realization forces a re-evaluation of theoretical models, pushing the boundaries of our understanding of black hole formation and growth. The findings also challenge assumptions about galaxy formation. The 11 galaxies observed in the CS survey, formed between 470 and 675 million years after the Big Bang, are not just relics of the past. They are living records of cosmic history, each offering clues about the interplay of stars, gas, and gravitational forces in shaping the universe. The early universe, often referred to as the Dark Ages, was a mysterious and poorly understood epoch. During this time, the first stars and galaxies were beginning to form, but their light had not yet ionized the hydrogen gas that filled the cosmos. The JWST's ability to detect infrared light has allowed scientists to peer into this era, uncovering details that were previously out of reach. One of the most striking revelations is the presence of heavy elements, such as carbon, in these early galaxies. These elements are the byproducts of nuclear fusion in stars, meaning that the first generation of stars must have formed, lived, and died far more quickly than expected. The supernovae of these population 3 stars would have enriched the surrounding gas with heavy elements, setting the stage for the next generation of star and galaxy formation. Black holes were not mere bystanders in the universe's early days. Instead, they were active participants, shaping their surroundings through powerful winds and jets of energy. These interactions likely played a crucial role in reionizing the universe, ending the Dark Ages and allowing light to travel freely through space. The JWST's observations suggest that supermassive black holes may have acted as engines of galactic evolution. By driving star formation and scattering elements, these black holes contributed to the rapid development of galaxies. However, their exact role remains a topic of intense investigation. Were they catalysts for growth, or were they simply byproducts of a universe undergoing rapid transformation? The discovery of complex organic molecules in galaxies that formed less than 2 billion years after the Big Bang is a groundbreaking revelation. These molecules, considered precursors to life, suggest that the universe was gearing up for biological possibilities far earlier than previously thought. For example, the JWST has detected polycyclic aromatic hydrocarbons, PAHs, in ancient galaxies. These molecules, which are cousins of soot formed on Earth, are key building blocks for more complex organic compounds. Their presence in the early universe hints at a rich chemistry that could have set the stage for the eventual emergence of life. The discoveries made by the JWST are not just rewriting the history of the universe, they are inspiring a new wave of scientific inquiry. Every observation, every spectrum captured by the telescope, adds a new piece to the puzzle of cosmic evolution. As we delve deeper into the mysteries of the early universe, we are not just uncovering the story of galaxies and black holes. We are exploring our own origins, tracing the cosmic threads that connect us to the stars. The detection of massive black holes like CS 1019 in the universe's infancy is a testament to the power of modern astronomy. These findings challenge our understanding of cosmic evolution, forcing us to rethink the processes that shaped the early universe. With the JWST continuing to reveal the cosmos in unprecedented detail, we stand on the brink of a new era of discovery. From the formation of the first stars and galaxies to the role of black holes in shaping the cosmos, the universe's story is far from finished. And as we uncover each new chapter, we are reminded of the boundless wonders that await us in the infinite expanse of space. Let me know if you'd like me to expand further into specific sections, such as detailed explanations of black hole formation theories, the role of reionization, or the implications